Let us start. All right. Okay. So yesterday we started a new kind of subtype of this proportional calculus. It's not exactly new. It's just logic and proportional calculus in a different context, which we call as Boolean algebra. Okay. So if I just quickly summarize, so what is Boolean algebra? So in Boolean algebra, what we are dealing with is we always deal with this set, Boolean set called 0, 1, and we apply different operations on this set, and we get the resultant statements or resultant expression. Okay, and how this is related to proportional calculus? There's a complete one-to-one correspondence between the Boolean algebra and the proportional calculus. The only difference comes from the notations you use and the context where it is used. Boolean algebra is primarily used in areas like circuit design, where uh, eventually, if you look at the circuit design, what you are dealing with is the bit, right, which can again take just two values, 0 or 1, right? So that again brings us back to our original proportional calculus, which is also based on just two values, true or false. Right, so if you look at the Boolean algebra, the kind of operations we are allowed to do, primarily there are three. You have complement, you have Boolean products, you have Boolean sum. Right, you had complementation operator, you had a Boolean sum, and you had Boolean product, and we discussed how each one of them works. Okay, and if you look at the mapping of how you can make the logical equivalent of any expression in Boolean algebra to a proportional calculus. So what is the mapping? Can anyone tell me? Instead of Boolean set 0, 1, what is the equivalent set in proportional calculus we deal with? Yes, class, what is the equivalent set? Let's revisit the one-to-one mapping we have in the proportional calculus. So if we have 0, 1 in Boolean algebra, what do we have in proportional calculus, class? Very good. You have false for 0 and 1 for true. What about complement? Which operator represents complement? Sorry, bar, or what you say, negation, right? What about Boolean sum? Or, and product is your and, right? So if you just make these replacements, then any statement you write in Boolean algebra can also be written in the proportional calculus, the equivalent statement. So after that, what we discussed was something called a Boolean function. Okay, now what is a Boolean function? A Boolean function of say degree n is a function uh, f from set b to the power n to b. Okay, so that means you take inputs which are n tuples, but ultimately what you map them to is just 0 or 1. That is the b set, right? So so we discussed that the various Boolean functions we have, we can represent various expressions using them. Okay, so if we have say primitive Boolean expressions, say b1 and b2, by expressions I mean combination of the value 0, 1 by applying some Boolean operations to it. And if we combine the Boolean expressions also, say by a Boolean sum or a Boolean product, the resultant is also a Boolean expression. So if you go on doing nesting of the Boolean sums and products at any sort of depth, the resulting will also be a Boolean expression, right? And what we had ended up on discussing was that Boolean functions can have a neat representation in form of n-dimensional cube. Okay, and I had asked you to do a very simple exercise wherein we map a degree 3 Boolean function to a three-dimensional cube. Okay, and I asked you, you should take x as the first coordinate, y as the second, and z as the third coordinate. Okay, did everyone try it? So the figure you see in this diagram, it did not have x, y, z. It had, I think, As far as I remember, it was, I think, y, x, and z, something like this. Okay, I had asked to make it in this manner. Did anyone try it? Okay. Okay, let us start with a simple two-dimensional one. If I have a two degree 2 function, okay, and I need to map it to a two-dimensional cube, okay, which is basically a square. So how can I do it? Okay, let us consider x comma y as our tuple. Okay, so I'll make this. Okay, so x axis is this and y is this. Okay, so what are the coordinates of this point? Remember, x axis is this and y is this. Very good. So x axis is 0 on this side. So you have first is 0, and this is also on this side of x axis. So it's also 0, right? Both of them are on the extreme end of the x axis. So both of them are 1, right? Now out y axis. So anything which is on the lower half is 0 and anything on the top is 1. So you get 0 and you get here 1. Right? Now similarly, if I have to do three-dimensional cube where x axis is this, y axis is this, and z axis is this. So can you tell me the coordinates now? Class. So tell me, what are the coordinates of this point? Yes, class, what are the coordinates of this point? Very good. It is 0, 0, 0. What about this one? So x axis is 0 here and it is 1 here. So 1, 0, 0. Very good. And this? So this one, x axis is 1, y is 0 because y is still on lower side, and z axis is 1 because z axis 0 is here and 1 is here, right? So you have 1, 0, 1. Excellent. Now what about this one? X axis is still on 0, y axis is also 0 because it's on the lower end, and z axis is 1. Okay, so that completes our lower half. Let's move on up here. So what about this point? X axis is still 0, right? Y axis is, y is here 0, here it's 1, so it's 1. Z axis is here 0, here 1, so it is 0. Okay. Similarly, what about this one? X axis is 1, y axis is also 1 because it's at top, but z axis is 0, right? 1, 1, 0. Right? Okay, great. So what about this one? X axis is 0, y axis is 1 because it's at top, and z axis is also 1. So what about the last one? 1, 1, 1. Okay. Is this mapping clear to everyone? This will be very relevant when we will come to lattices. Okay, that's like the last module, but is this mapping clear? Yes, class, is this clear? What about others? Is this clear? Okay, great. So now let us proceed from here and discuss some more things about the Boolean function. Okay, so when we consider now the Boolean function, so suppose I consider two Boolean functions, a Boolean function f and a Boolean function g, which has say n variables. Okay, now given two Boolean functions f and g, okay, and since both of them have n variables, means both of them are degree n, we say that two functions are equivalent if and only if the following condition holds. What is the condition? If you consider the f applied on b1 to bn, the n tuple, and g applied to b1 to bn, they are exactly the same. Okay, whenever b1 to bn belongs to b. Okay, so what does it mean? Basically, whatever input values, whatever input combinations you give to each one of the functions, the resultant output should be same. Okay, so if the two Boolean functions are same, So basically the expressions representing those functions will also be same. Okay, like I can give you an example. Suppose if I write x Boolean product y and I write x Boolean product y plus 0. Okay, if I do a plus 0, what is the resultant output? If I do a Boolean or Boolean sum with any literal with a 0, what is the resultant? You can map it to proportional calculus. We are saying doing a or with false. Okay, so if I do or with false, what it will return xy back, right? So this is equivalent. Similarly, if I do a xy Boolean product 1, it will also give me xy. So all three of them, they may look different, but if you give them any input combinations, their answer will be same. Such kind of expressions are known as equivalent Boolean expressions. Okay, is that clear, class? What is the equivalent Boolean expression? How do you find equivalent ones? You can check that if you like someone asks you a question, check whether the two are equivalent or not. Okay, so the way you can do it is you can make a kind of truth table, take all possible combinations of the values, okay, and then see whether the truth value of the resultant expressions is same or different. Okay, so that's how you can check whether two Boolean expressions are equivalent or not. Okay, so that was how do you prove that two Boolean functions or their expressions are equivalent. Now, like we see in sets or in proportional calculus, we can negate a complete proportional, complex proportional statement. So can we do complementation of Boolean functions as well? Okay, so this is completely allowed. If you have a Boolean function, say f of x, y, z equal to say x, y, z plus x, suppose. Okay, now if you want to do complement of this function, okay, the way you can do complement is you can take the complement inside the function. Okay, so complement of a complete Boolean function is taken by taking the complement inside and applying the desired rule. Okay, so complementing is not just allowed for Boolean variable but also for the Boolean function. Okay, and we'll see shortly some rules which will help you in this. Okay, similarly, like we discussed yesterday, we can combine two Boolean expressions. Same thing can be applied for Boolean functions also. If you have two Boolean functions of same degree, you can calculate their sum or their product. Okay, their sum or product will simply be the sum of their respective Boolean functions or product of their respective Boolean functions. Okay, so like long story short, from these two slides, what you infer is two things. Every Boolean function can have an equivalent Boolean expression, and all the operations you can do on Boolean expressions can be done on Boolean functions as well. Okay, whether it's negation, whether it's complementation, whether it's Boolean sum, or whether it's Boolean product. Okay, so all of them are valid operations, whether you do them on Boolean expressions or you can do them on Boolean functions. Okay, and where do you get this connection? You get this connection because of the fact that every Boolean function can be represented as some expression. Okay, like I can show you, like suppose I have a Boolean function, say from B3 to B, I can write it as an expression. Like I can give you an example, suppose x, y, z is equal to xy plus z. So this is a Boolean function of degree n. Okay, so every Boolean function can have an equivalent Boolean expression and both of them have valid operation. Okay, is that clear, class? The relation between the Boolean function and the Boolean expression? Yes, class, is that clear? Okay. Okay, so let us move forward and try to see how can we count or how can we keep a track of how many Boolean functions can we actually declare of a particular degree. Okay, so before I generalize it to degree n, let us consider a simple case wherein I have a Boolean function of degree 2. Okay, so let's try to break it down. I have a Boolean function of degree 2, means the function is from b square to b. Okay, So if the function is of degree 2, how many possible input combinations do I have? Degree 2 means 2 inputs, right? But how many possible combinations will be there for 2 inputs? Excellent. There will be 4 possible combinations, right? Which you can see here, 1, 1, 1, 0, 0, 1, 0, 0. Okay. Now we want to see how many possible Boolean functions can be there which are of degree 2. Okay. How do we determine that? Now we know that what Boolean function does is it maps the tuples, or in this case pairs, to a value 0 or 1. So all these 4 combinations, they can have what kind of values? Either they can be a 0 or they can be a 1, right? So that means each of these 4 combinations can take 2 possible values, either a 0 or a 1. So all possible combinations that you can have are 2 to the power 4, right? How do we get that? First step is, if there is a function of degree 2, means it takes 2 inputs, what are the possible input combinations? Okay, so input combinations we have are these 4. Now out of these 4, each one of them can sometimes be true, sometimes be false, right? Each of the combinations can sometimes be true or sometimes false. So each one of them can take 2 possible values, either a 0 or a 1. Okay, so if you look at all possible combinations using simple counting principle, the total possible functions are 2 to the power 4, right? So like you can see, all of them have been listed here. Sometimes all of the terms can be 1, sometimes say one of them is missing. So if you count the all possible combinations, the total possible combinations are 60, right? Now if I have to suppose generalize it, okay, to Boolean function of degree n. So can you tell me, given a Boolean function of degree n, how many total different Boolean functions can I create of degree n? Use the same logic. First see what is the input to the Boolean function of degree n. Then see the possible input combinations. And then see the total Boolean function based on the fact that each term can be 0 or 1. Okay. So tell me, how many possible degree n Boolean functions can you create? Use the same chronology of steps. First, see, if I have a Boolean function of degree n, how many inputs will it take? That's correct, Hasib. Let's do it step by step. If I have a Boolean function of degree n, how many inputs can it take, class? No, not all possible. I'm just taking the inputs, right? So if I have, suppose, f from b square to b, what is the input form? How many inputs does it take? 3, 2, how many? Just 2, right? No. So this one, I'm saying degree n in general. It is n, right? Any degree n function takes n as input. Now, if you look at all possible input combinations, they are 2 to the power n, right? Now, all of these input possible combinations can either take value 0 or 1. They may be present or absent in a term. So, from the simple counting principle, it is equal to 2 to the power 2 to the power n, right? So that is the general formula, or to get how many possible different Boolean functions you have. 2 to the power 2 to the power n. Okay, let me just repeat. Where do you get this hierarchy? So first thing is, if I have a function of degree n, how many inputs does it take? So like here, degree 2 function, 2 inputs it can take. So general degree n can take n. Now, what are the possible input combinations? They are always 2 to the power n, right? Like in this case, they were 2 to the power 2, which is 4. Now, each of these terms, for all these conditions, they can either be present or they can be absent. So each of these 2 raised to n terms has 2 choices, either to be present or absent. Okay, and that is what brings us to 2 to the power 2 to the power n. Okay, is that clear? So this is the table which summarizes that if you have a degree 1 Boolean function, so there are 4 possible Boolean functions. Similarly, if you have 2, then you have 16 possible, and so on and so forth. With just slight increase in degree, the number of possible functions increase tremendously. Okay, it's 2 to the power 2 to the power n. Okay, is that clear, class? Is this clear to everyone? Okay, so we can have a look at the degree 1 all possible Boolean functions. So for degree 1, they have just one input, right? So one input means how many possible combinations? Yes, class, how many possible combinations? If I have just degree 1, 2, so 0 or 1, right? Now let's see what are the all 4 possible functions which they have stated here. Okay, you can have both of them on, both of them off, one on, one off, one on, one off. Okay, so how can you tell me the equivalent Boolean expression? If I write f1 is 1, 1, what does it mean? Okay, so that's what we'll do today, how to make a Boolean expression out of a Boolean function. Okay, so these were the all 4 possible combinations, and that's what we'll see next, how to make a Boolean expression out of these forms. Okay, is this clear? How to find Boolean functions of degree n in general? Yes, class, is this clear? Okay, great. Okay, so before we go to how to make Boolean expressions, let us go to the various popular identities of Boolean algebra. Okay, so again I am repeating, this is nothing new. These are going to be all same laws which you have seen in set theory when you were discussing proportional calculus. Okay, now only the context and operation style is changed. Okay, so let us see what are the standard laws of Boolean algebra, and like what do we infer from all of them. Okay, so first Boolean identity is known as law of double complement, which says that if you take the complement of a Boolean expression, it will give you the thing back. Okay, which is same as your complement law. If you take the complement of a set, it's going to give you the set back. Okay, the next category of laws are known as idempotent laws. That is, if you take a Boolean sum of similar variables, it's going to give you the variable back. Same thing applies for the Boolean product. Okay, and it's a very important law to use, because sometimes when you need to prove something, you can simply replace this x by either a Boolean sum or Boolean product depending on your need. Okay, so idempotent law is very important in that sense. The next categories of laws are known as identity laws. Okay, identity law, what it basically says is, if you take various operations, whether it's Boolean sum or Boolean product, what is the element that you operate on such that you get the expression back. Okay, so in general, identity element, as we'll study later in group theory, is that element which when applied with some expression along with an operation gives you the element back. Okay, so if I have to consider Boolean sum, what is the element which when added will give me the expression back? Okay, we know for Boolean sum it's 0. If you add 0 to any expression, it's going to give you the expression back. So 0 is known as the identity element for the Boolean sum. Okay, similarly, what is the identity element for Boolean product? One is known as the identity for the Boolean product. That is, what do you mean by identity? Identity in general for any operation means that element which when applied with the given operation gives you the expression back. Okay, so that was identity law. Next is domination law. Okay, what do you mean by domination law? Domination law basically means that irrespective of what the value of expression takes, your answer is always going to be the same. Okay, so if you recall from proportional calculus, if I take any value of proposition, right, and I take it OR with true, what is it always going to give me? If I take any proposition and I take its OR with true, what is going to be the result? Okay, and what is this known as? Remember, there are, if you have any propositional statement which every time gives you a true value, irrespective of what is the input, what are such kind of statements known as in propositional calculus? Excellent, excellent. Tautology, right? Similarly, you have, if I have a P and I take its intersection with false, it's always going to be false, right? And what are such expressions known as? Yes, class? Sorry? Tautology, and what is its opposite? Very good, Daniel. Contradiction, right? So, tautology and contradiction actually are the other forms of domination law. That is, irrespective of what input you give, you're going to get a 1 if you do a Boolean sum with 1. And if you do a product with 0, you're going to get a 0. Okay, and in proportional calculus, it maps back to tautology and contradiction. Okay, and one more thing which I kind of missed in between. So, if there is some statement for which it's not always true or always false, such are known as contingencies. Okay, like if I write P and true. Okay, so P and true, can you say what is the answer of this in general? I cannot say, right? Because if P takes the value of true, then it's going to be true. If P takes the value of false, then it's going to be false. So such statements where we are not sure whether they are going to be true or false, and it depends on the input, such are known as contingency. Okay, so contingency is something which is between tautology and contradiction. Okay, so coming back here, so these two expressions denote the same, tautology and contradiction, or domination of 1 and 0 when you apply them in such a way. Okay, is this clear? Tautology, contingency, contradiction, and domination laws. Yes, class, is the mapping clear? Okay, great. Now let us see some more laws. So like set intersection, set operation, and all, the Boolean sum and Boolean product are also commutative. Okay, so you can flip the order and it will not affect your expression, and they are also associative. Okay, you can take them in any order and the result will be unaffected, and they also satisfy distributive law. Okay, so Boolean sum distributes over Boolean product, and Boolean product also distributes over Boolean sum. So all these laws are very well hold for Boolean algebra as well. Similarly, the De Morgan's law, okay, the negation law also holds for this. So if you take the negation of a Boolean product, like we had in set theory or in proportional calculus, it will do two things. One, it will change the operation of product to sum, or if it is sum, it will change to product. Okay, and it will take the complement of the individual element. Okay, so x Boolean product y complement is x complement Boolean sum y complement. Okay, and vice versa if you take it for the Boolean sum. The next property is known as absorption law. Absorption law is again a very powerful proven technique. So what absorption law states that if I have a expression and I take its Boolean sum with the Boolean product of that expression with some other expression, the other expression is going to be absorbed. Okay, same applies if we take the Boolean product. If I take Boolean product of expression with the Boolean sum of that expression with some other expression, the other expression is going to be absorbed. Okay, and the last two properties are the complement form. That is, if I take a Boolean sum of a expression with its complement, it's always going to give me 1. Okay, and if I take the Boolean product of an expression with itself, it's always going to be give me 0. Okay, so these are some of the standard Boolean identities, which are again nothing but a one-to-one correspondence of things you have already seen in set theory or in proportional calculus. Okay. Any questions from these laws? So like if you are curious, like where is it used? So like in proportional calculus, if you want to prove some statement, or in set theory, if you want to prove some complex statement, that is where they are used, the standard identities. Okay, and we'll see on next slide one such example. Any questions, class, till this point? Okay. So let us see this one very simple example of where the standard identities can be used. Okay, so you can see standard identities can be used to prove each other as well. Okay, like here the question here mentioned is prove the absorption law using the other identities of Boolean algebra. Okay, so let us see how they have done this. So we have expression x taken with the Boolean product with the Boolean sum of x plus y. Okay, so first thing that we can do is we can replace x by x plus 0. Okay, what is this identity? This identity is known as identity law. That is, as I had mentioned, this is a very powerful thing, one of the powerful laws in proving technique. To replace a single variable by a Boolean product or Boolean sum. Okay, so you can see I have replaced x by x plus 0 by using the identity law. Okay, now I have two Boolean products of respective Boolean sum, right? So here I can use the distributive property because x is common in both. So I can distribute the Boolean sum over Boolean product and I can write it in its condensed form as follows, right? Now we know we have an identity that any expression of Boolean product with 0 is 0. Okay, to bring it in this form, we can use the commutative property. 0 Boolean product y is same as y Boolean product 0. And we know from domination law, y into Boolean product 0 is 0. And from identity law, we know x plus 0 is x. So you get this result. Okay, so this is not that very easy to take off. I mean, if you practice more expressions, you'll get an idea where to use what. Okay, but for all of that, you need to have an idea of what are the various Boolean identities and how to use them. Okay, so I'll be sharing some tutorial questions wherein you'll get the desired practice. Okay, now let us move next to again a very important concept which we have been seeing throughout in the first two lecture modules called duality. Okay, like you have duality in set theory, like you have duality in proportional calculus. Since Boolean algebra also comes from them, so Boolean algebra also satisfies duality property. Okay, and what is the duality property? Duality property simply tells you that you can take a dual of a Boolean expression by doing some interchange. Okay, what are the interchange? Wherever there is a Boolean sum, you replace it by Boolean product. Okay, and vice versa. Both are allowed. And wherever there is a 0, you replace it by 1 and vice versa. Okay, like for example, if I have these two examples, I have a Boolean product of x into y plus 0. Okay, so if I have to take its dual, how do I find the dual? Yeah. So let me bring it here so that you can try and not see the answer. Okay, can you try the dual for this? Remember, wherever there is a 0, replace by 1. Wherever you see a product, you replace by sum. Okay, so we can start right from here. So we have x, we have a Boolean product here. Okay, so Boolean product can be replaced by a sum. Okay, then we have a Boolean sum here, it can be replaced by a Boolean product. And finally, you have a 0, it can be replaced by a 1. Right? So next is x into 1, y plus z. So can you tell me the equivalent of this, the dual of this? Yes, class, the dual of this, x into 1 plus y plus z. Okay, great. So X Boolean product replaced by sum, 1 replaced by 0, sum replaced by product. Okay, great. So these were the duality laws. How can you make a dual of a given expression? And the way you can do is by simple interchanging of Boolean sum by product and 0 by 1. Okay, so I'll end on this slide today. So if you now formally define Boolean algebra, what is a Boolean algebra? In general, a Boolean algebra is defined by the following manner. You say the Boolean algebra is a set B, okay, which consists of two binary operations. Binary operation means which take two inputs, okay, and element 0, 1, and a unary operation bar. Okay, unary operation means which takes just one input, and all these properties hold. There is identity law, okay, there is complement law, there is associative law, there is commutative law, and distributive law. So any set B, which along with these operations holds true all these properties, we say that such a set is known as a Boolean algebra. Okay, so this slide, even if you don't understand, we are going to come back to it in group theory, and we'll see lattices can also be used to represent Boolean algebra. Okay, anyone remembers what is lattice? We had discussed this like very briefly in one of the lecture modules. Sorry, little louder. What is a lattice? Anyone recalls what was a lattice? Right. I just don't need the exact definition. I mean, what was it related to was when we discussed pre-order, right? When we discussed pre-order, that's somewhere a special case of those is a lattice. Okay. So I'll stop there. We'll proceed to quiz, and then in next week we'll start with the remaining parts of it. Any questions, class?